Yeah, so basically I've tried to put together a collection of problems that kind of go in three groups. The first one I call the kind of traditional interaction between these methodology streams, and I'll tell you what I mean by that in a second. But as we build up, I'll work towards kind of newer ways that we found in which you can get computations and analysis to help one another. So just to kind of introduce myself for those of you who don't know me yet, I tend to work on problems that are quite messy, quite multi-scales, and quite non-linear in spirit. And my specialty is really in the high-performance computing side of things. So I did my undergrad degree in Germany at the University of Bremen, and it was a degree in applied and computational mathematics, which was really at the interface between computer science and applied maths in the traditional sense. Part of that is we also did internships, and in my case it was in a medical imaging facility. So I worked a lot in computational acoustics and finite elements at the beginning. And then I got to Imperial for my postgraduate years. I was very luckily assigned to Darren as an academic advisor at the time, who promptly then introduced me to Dimitrios, whom I worked with for 6 years, I think, during MSc, PhD, and postdoctoral years. And yeah, during that time, I think I worked a lot on liquid films and electrohydrodynamic type flows, but later on I got into drop impact problems. Both of these topics will feature among the problems we're going to talk about today. And especially as I got into the drop impact side, actually, two of the organizers of this workshop, Sasha and Jose Manuel Gordillo, have been highly influential figures in my career. And the other main organizer, Mark, was my external thesis examiner. So this is a very kind of, a very micro type of element of situation. Yeah, for the past 5-6 years, I've been lucky to work with Susanna and to co-supervise Oscar together, and I got to work a bit more in control, which is actually where I'm going to finish off today in a nice and symmetric way as well. So what I'll try to do during the first session of the day is talk to you about kind of my way of thinking around these problems, and hopefully instill a bit of inspiration as to how you can get a bit of computation to help rather than hinder the process along. And I'll definitely do it in the spirit that I quite like Basilisk as a mechanism, like as a pedagogical tool, but I'm hoping that we'll do it in a way that even if you prefer other bits of software, the elements we're going to learn about will be useful regardless. So that's, I think, yeah, you're welcome to tune along even if you're not Basilisk fans quite yet. But with that in mind, I'll share a bit about how the research group was built, because that will give you a sense of how the problems evolved. So I mentioned, yeah, that there are two sets of problems in there, some pertaining to the drop dynamics, so bouncing, splashing, and so on, all fairly violent interfacial flows. So they're the types of problems that where things happen quickly, we don't know much about them, and we're trying to resolve complicated dynamics in a way that gives us information about it. The other side of this with the liquid films, things are a bit gentler. You can think also of microfluidic context and so on. I think many of the solutions, if you leave the systems as they are fairly mature and well known, the difficulty there is to get them to do what you want. You kind of have to poke them with a stick and say, do something. And in this case, our stick can take the form of electric fields, magnetic fields, injection, blowing, suction, things like that. But the idea there is that they become quite multi-physics. And it's that stream that we developed a bit more in terms of control theory, equation discovery, and so on as well. So these are the 5 PhD students that were working in the group so far. Everyone holding a thesis has graduated. Oscar is the next in line. And Michael and Ben did their work in Oxford with me on drop impact projects. Oscar, as you've seen, has been working on control theory for thin liquid films. Seb is co-supervised by myself and James Sprittles and our colleague Albert in chemistry, who's a specialist in machine learning, and he's working on equation discovery. So it's this idea that you have data sets that may come in from either simulations, whatever they're done in, or experiments, but they're in regimes where you cannot derive the equations from first principles. But you may know something about the problem. So you may expect, for example, surface tension or diffusion or any known physical effect to play a role. So you can basically physics inform part of your equation and then use the data in order to infer the nonlinear part of the equation that would be difficult to derive from purely, say, asymptotics grounds. And this is not with the intention for it to be a black box, but really to try to push asymptotic models as far as possible. So we're looking now into getting into thick film rather than thin film asymptotics in the one limit of this, where we still have some hope of gaining intuition of what happens. But because you've seen James's talk the other day, we're also looking at very thin film problems, so thin that the continuum assumption starts breaking down, then you start having to include fluctuating hydrodynamics and kind of stochastic terms, where again, it's still an equation we know and love at heart, but it'll have a term that presents itself with some difficulties that we have data from. So that's kind of the spirit of what Seb's looking into now. And Min has just started very recently, and with her we're looking at bioreactor projects. So this is something under a sustainability theme. We're looking at alternative protein sources, cultivated meat modeling, the first stages of which are an interfacial flow. It's essentially half-filled bags that are agitated in a particular way. And it's kind of a new industry, nascent problem space. And not a lot of fluid mechanicists and applied mathematicians have looked at it, but it's still pretty much a controlled theoretical shape optimization fluid mechanics problem that's quite rich and pretty much untapped. So it's nice to do. And the kind of special effect on this one is if you kind of work through the full set of timescales, you'll get cellular growth involved as well, and there's nice ways to introduce agent-based models and then other types of more sophisticated models therein. So as you noticed, everything falls under the theme of interfaces. It just matters what flavor of multi-physics and complication you would like to pick. And just to give you a sense of where some of the students went, I did prepare a few background things. So Michael, I mentioned earlier. So Michael started off a company called Vanillus. It's machine learning / AI enhanced CFD formulations. Oscar worked there for a few months earlier this year. And they're really looking into kind of scaling up the speed through which we can do certain things for industrial processes, particularly at higher Reynolds number ends and so on. But yeah, they've had a growing theme. They went through an entrepreneurship program, and I was happy to see that they're thriving. Suzanne and I visited them a few months ago, and everything's going nicely there. So yeah, if you're interested in that as a career aspect, do let us know. We're happy to tell you what we know. Ben's currently doing his postdoc in Oxford together with an experimental colleague of mine, Alfonso Castrejon Pita, and myself on the computational end. So yeah, it's a really nice team. And we do work quite a bit with industrial mathematics, and I'll touch upon that in kind of during the talk when I can, and under the theme of sustainable software engineering as well. I believe quite strongly in open source software and kind of community level coding, which is why the latter part of the day will work in that spirit as well. But this is, yeah, the gist of the operation in some sense. Cool. So I mentioned, yeah, I'll try to give you 3 flavors of ways in which analytical formulations can interact with computational ones. And what I mean in this case by the traditional framework, let me see if I can find, yeah, we have an eraser here. So if I think of a typical asymptotics friendly setup, no matter what parameter we do it in, say this is the 1 space, and somewhere here there's a parameter epsilon. It can be an aspect ratio, it can be any kind of parameter of interest that exhibits a multi-scale nature that we can sort of expand on and derive a simpler version of the model that is more tractable. And in many cases, we know that models tend to be valid as long as you're within the range of the validity of set assumptions, usually when epsilon is sufficiently small, loosely speaking. Now, it so happens that if you want to do something like a direct numerical simulation, actually going to really small numbers, really large aspect ratios and so on, they're very difficult cases to do, even with bells and whistles like adaptive mesh refinement and so on. So the happy place for your typical DNS, this is black, I think I want the green, but I may not have it. Let's work with it. We can make it work. Yeah, somewhere here, maybe a bit more. The idea is that as long as numbers are order 1, you're actually quite happy. And of course, philosophically, you can extend this as much as you want. And what we try to do as modelers is to come up with progressively better models that pushes this over the line, kind of in this direction. And what we try to do numerically is to have progressively more efficient and better computations so that we take this over a nominal line in this direction. This leads us to an ideal region of overlap in which we can cross-validate the two. So if you have this type of scenario, it means that, well, on the one hand, you can test your model. So you can see that the analytical side of things has support through a different methodology, and the type of simplifications that you've made still produce viable results if you believe that this is all you need in the world. On the other hand, it also lends a validation framework for your computations. If the difference between computational fluid dynamics and colorful fluid dynamics, pretty pictures are not enough to get viable results. You do want always to check. But basically, in the absence of everything, there are mechanisms to do self-verifications of things, but as long as we have other methods to work with, analytical methods and experimental data, then we should work quite hard in order to develop trust in what we're trying to achieve. And on top of all of this, in an ideal world, if you do have nice colleagues who run experiments, and you're able to put data points on there that overlap with everything, then it means you have a reality check, like a real reality check on top. So, but what I mean by the traditional multi-prong framework is, if you have all of these three things, you can then basically use models that are quick, efficient, and really good, that work where DNS cannot get, to essentially tell you where you're hunting for kind of interesting behaviors and canonical type of behaviors. You can use the DNS once validated to push in nonlinear directions where the model cannot get, because then it's outside of its range of validity, and you can have confidence in both because there's experimental results to back this up. And on the other hand, now you can help the experiments, because quite often if you do experimental studies, you have cameras, you have sensors, but there's only a discrete amount. You can only see certain things in experiments. So for example, you can look at interfacial shapes, or you can look at the pressure sensors at the bottom of a pool, but you will never get kind of a full resolution pressure velocity field and full resolution for interfacial shapes either, in kind of dead angles and so on. So the idea is that once you've established that everything is okay, you can use it strategically to then fill some gaps in the experimental understanding of the picture as well. So to make that come to life, I have picked the problem of bouncing droplets. A, because it's kind of nice and gentle, and secondly, I quite like the collaborative space this offered over the years. So if you think kind of impact problems in general, then you can kind of exhibit maybe 3 or 4 typical behaviors. Like if you've seen this type of stuff before, you may think, okay, you can get coalescence, you can get splashing, I've alluded to bouncing. There are other interesting things that maybe are not quite as familiar. So this is a so-called coalescence cascade, where what happens is there's always going to be a thin film of gas in between the drop and the pool as it's impacting, but as the droplet rests on it, it drains out, and eventually it's so thin that it coalesces. However, the volume is quite small and the surface tension is strong, so it's enough to restore its shape to the spherical one, and you've seen that it's still bouncing, although I've rambled on for a minute or two, and you can get this going for, more bounces than you expect. So it's quite a rich landscape, and there's lots going on there. But in general, this impact space gives us a few problems to lean on, and it'll kind of be the topic of the next 2-3 problems actually I'm going to talk about. But we can start with bouncing first. So this is the team we've been working with. I was lucky to meet up with colleagues at the University of Bath, Paul Milewski, who's a good friend to many of us, and his student at the time, Carlos, who's now in academia as a lecturer as well, and the team at Brown University, Dan Harris, and really good PhD and undergraduate students working in his lab. All kind of 3 groups appreciate modeling, and then the specialties are Dan's group runs the experiments. Paul has a fantastic model that I'll walk you through that he's been developing with Carlos and other students over the years, and I helped out with the numerical side of things. So with that in mind, I'll start by describing each and every one of them in brief detail. So the typical experimental setup looks something like this. You'll have a container, a drop generator on top of it, and a camera and a lighting system. And Dan's really nice in designing very usable type of tools. So if any of you work within experimental spaces and, for example, would like to set this up in a local lab, we're setting one up at Warwick kind of as we speak this summer. And through these types of papers that have ample supplementary material, Dan's pretty much created one that you can 3D print in full, except for tubing, and $200 plus the cost of living crisis increment, let's call it $300 for the argument's sake, is all you need to have a setup of this type that really produces reliable droplets on demand, which is really nice. So the type of drops bouncing that I would like you to have in mind looks something like this. And what I want you to really focus on and how much the drop is deforming. So it's a spherical drop approximately to begin with. I'll play it again anyway. It's hitting the pool, and as it does so, it flattens. It became something like an oblate spheroid, and then it undergoes the same type of coalescence cascade I showed you before. But if you really focus for a second, on the shape of the drop as it hits, this is what we're going to try to model as well as the deformation of the pool as we migrate through the problem. So this is what we're getting from experiments, and just if you're curious, this is the type of parametric setup we're working with. So in a nutshell, we're using water and silicone oil, and I will just highlight the dimensionless groupings. I think the key bits to look at is really bond and Ohnesorge numbers are really quite small. So gravity and viscosity are not anticipated to play an important role in this problem. The Weber number is order 1, and the Reynolds number is quite high. So if we're thinking about designing mathematical models, these are some of the considerations we need to put in place. And droplets tend to be in the sort of submillimetric hundreds of microns type of range, just to kind of set the system in place for us. Great, so that gets us into the model. And since we're in a mathematics workshop and we're in a modeling theme anyway, I thought this would be the best time to sort of bring out my inner millennial for our first activity. Because you got to know me at the beginning of the presentation a bit, and I think I know many of you, but not everyone. So I have a little platform that I've set up here where if you to this website, which is polev for poleverywhere.com, my name 440.com, or just do this QR code, where it's going to be the same link for every activity. So once you get it once, you're fine. Don't worry about the effort of typing something every time. And what I'd like you to do as fellow mathematicians is just type in 5 or so keywords that you think would describe kind of what you do. So if it were me, I would say droplets, liquid films, DNS, asymptotics, EHD, for example, or control. Or depending on where I give the talk and who I'm talking to, I may change my keywords ever so slightly. And as you do this, they'll appear and we'll get a word cloud of basically what folks in the room are doing. I thought I'd do this because you knew you had to have laptops with you, and it helps with the smartphone attention span as well. So yeah, I kind of keep a collection of these, and I'm always curious what crowds are kind of merging towards in terms of topics of interest. You got a few replies in. What are we getting? People like mechanics. Fluid mechanics, pretty good. PDEs, asymptotics. But otherwise, okay, it seems like we're not getting fairly heavy weights in a given direction. Quite a few, yeah. Now, very good. I see Sarah and John are active on the system. It does have a limit of, I think, 25 participants or so. So I think maybe at some point it may not let us do this. But I think, yeah, this gives us a pretty good picture of who we are. I'm sorry, Jack. You have to be quicker next time. There'll be a few more, don't worry. Cool. So this is kind of what we do. It gives me a good impression of what type of modeling approaches we are interested in. And yeah, what we're going to do here is basically work through a model that allows us to simplify things enough so that we can solve the problem in, say, up to a minute in computational time. This is kind of the goal of the model. And to do this, the list of assumptions that we need to look into are like this. Easy ones are, we assume the pool to have infinite depth and infinite width. We assume, I think the critical assumptions here are really the last two. Basically, we will derive a linearized model, and we will assume only relatively small deformations of the drop. So if you remember the image I showed you from the experiment, we'll be able to capture elements of that, but as soon as that deformation is no longer relatively small, loosely speaking, we may not expect this model to be valid anymore. The good news is we have 15 plus years of good history in this problem space. People have been interested in impact type problems for a while, so we have a good analytical foundation. I'll derive it in 2 steps. The first thing I want to do is, rather than doing it with a liquid droplet, I'll do it with a perfect sphere, because then it'll allow us the full view of the pool equations without further complications. And once we get the pool equations, then I'll make the droplet deform as well. That's kind of how we ran through the problem. Actually, the first study we did with the team was on the superhydrophobic sphere, and then we turned the sphere into a drop. So that's why you see some of the nodes down there. And with the typical notation that we may be familiar with, if I'm going to write the velocity potential as phi and use eta for the free surface elevation, you'll notice that, if I assume that that Reynolds number is sufficiently high, and if I assume that I can take the potential in question, then all I get is a Laplace equation for the flow field inside the pool, and then you get typical kinematic and stress balance conditions for everything else. If you crank through the motions for a few pages, it really all boils down to the principal value of this singular integral. You need all of those assumptions I mentioned earlier to make it work, because you need some smoothness assumptions to actually operate it, and a bit of an adaptive algorithm just for the integration itself. But it's actually quite okay. You get there via Dirichlet to Neumann mapping, because the term I highlighted is really the only one that connects the Laplace equation to the rest of the conditions. So it's a fairly natural formulation, but it's one that kind of takes a bit of work to develop. And now if I try to put in a sphere in place, you'll notice I'm just using classical mechanical principle, so Newton's second law. You get an equation of motion of this type, and the type of conditions I have to kind of do the matching at the boundary. By the way, this is called the full kinematic match model, because it assumes a region of contact where the bottom of my sphere knows where the pool is. You don't want to have kind of volume overlaps or interface overlaps. So we assume that the top of the pool, in this sense, doesn't interact with the bottom of the sphere. They'll press on it, but they will never touch. And the angles are around 180 degrees, around this region here, so that it's a nice smooth exit from there. But otherwise, the key bit here is these terms that I've highlighted show you the interaction between the two. Essentially, the droplet, depending on its size and so on, exerts a certain pressure on the liquid pool, and the liquid pool feels it via suitable interfacial conditions. And provided you are happy to run an iteration through these conditions and make it happy in terms of continuity, smoothness, and so on, then you can design this to work in minutes, which is nice. So I can actually show you, I think, maybe on this one, what a typical realization looks like, experiment versus said model, which is axisymmetric. So it's not perfect. You'll notice, they're not exactly in sync anyway, but by and large, they work quite well. I quite like this because you notice that the sphere is fuzzy. It's coated with a superhydrophobic spray, and it kind of keeps that gas film in place anyway. But yeah, we were quite happy with the model in question at the time. And now I promised, now we're going to take the fuzzy sphere and make it a droplet. And in order to do that, we're going to decompose it into spherical harmonics. And because we work axisymmetrically, we can simply boil it down to Legendre polynomials. So you end up solving a system of equation for the amplitude of these modes, which is fairly nice to do in your typical solver of choice. And you can bring everything together through an energetic argument, which perhaps is more detailed than is needed anyway. And I guess in the same category, I'll just note that in order to make some of these things work, these assumptions come into play. So this only works for an honest source number, which is sufficiently small. And the good news is that based on the experimental parameters I showed you, we are in that happy place at the moment. The difficult bit in this problem is always that pressed surface area. And actually what we've done in this problem is we traded some accuracy for some simplicity. So instead of doing what I call the full kinematic match, where you do it everywhere on the bottom side of the surface, this is called the one-point kinematic match, where you match the south pole, but then you assume you measure the contact radius. So it's technically a two-point kinematic match, really. You need the south pole and you need the extent of the contact region, but then rather than calculating it, you assume a pressure profile. We have good information on this, by the way, in the sense that I'll show you later, but based on DNS calculations and so on, we know that something like a top hat profile works quite well in this problem. The pressure underneath the droplet tends to be constant, and then as you leave the contact region, it becomes flat as you go into the ambient region. So the reason why this is a particular choice in degree of polynomial is really to mimic a shape that looks something like this that we've tried to work through based on these principles of looking through a different methodology. So this is a scenario where the model already interacts a bit with the DNS, and I'm foreshadowing a little. Cool. And now I'll tell you a bit about the numerics as well. So we got the experiments in place, we got the model, we need the DNS. I've worked with Jeris since I think 2012 I started. And Basilisk is the younger brother of Jeris that started being developed, I think, in 2015, 2016. And now Jeris is no longer maintained, and Basilisk has been the mainstay in the community for about 5+ years now. So if you've looked through the Basilisk website, you'll notice maybe there's a bibliography section and so on. There's quite a bit of activity. There's a user forum. I'll show you through the ecosystem after lunch a bit more so that you know where everything is. But this has helped quite a few people, and the core development group is in Paris through Stéphane Popina at the Sorbonne University, but there's pockets of developers all over the world. The group's in Seville, Princeton, in Australia. We work quite a bit with it in my group as well. In general, I think it's proven quite versatile over the years. And the nice thing about it, so it's a finite volume package. It's second order adaptive in time and space, and for interfaces it uses the volume of fluid method. It uses this sort of quad tree in 2D, oct-tree in 3D structure, and it does so because of convenience in kind of spatial adaptivity reasons. It basically builds these type of trees that are really easy to allocate to processors, and it can do things efficiently, and then you need to build the interface on top of it, basically deconstruct it and reconstruct it at every time step depending on what happens. The advantage for this is that because you have an implicit object, you can think of your classical level set methods and so on, or in this case, a color function for the volume of fluid method, it naturally preserves mass conservation properties, even in cases with topological changes. So if you have a problem with ruptures, with coalescence, splashing, and so on, this is a framework that, at least in the right limit with the right resourcing, gives you some hope that you can accurately extract what you want from the problem. We can contrast this with, for example, an unstructured mesh, like a finite element type of process, where if you have some specific geometry, you can really kind of blend your elements to match the boundary. This gives you great accuracy, and kind of you can solve prototypes, and like if you want to flow, to model the flow around an aircraft, for example, using a finite element mesh is much more convenient than this. This will not quite accurately resolve the embedding if you try to put a solid geometry in there, but that respective finite element formulation would likely require surgery or some form of artificial cutting or merging of the interfaces that is less physical. So you'd have to decide it at the algorithmic level. So I think, and this is perhaps an important point, I really encourage you, no matter what you do, to try to kind of get 2 or 3 software pieces under your belt in terms of capabilities. Because if you only have a hammer, most problems you look at will look like nails. If you have a hammer and something else, all of a sudden you can unlock a few new classes of problems. So I've been lucky enough over the years to spend a bit of time in various groups, and 2 summers, 2011 and 2012, I think, I worked in Manchester with UNFLIB for my computational acoustics projects. So I learned a bit of both. You may have heard of UNFLIB through James's talk the other day. I'll talk about it more in the session beyond. But I think we'll walk through this in more detail for today because it's relevant for the topic, but really I think it's important to arm yourselves with as many software kits as possible, not just for the sake of it, you're not collecting them for fun, but if they're well complementing one another, you can really do a lot of classes of problems. Or in simpler terms, Basilisk is really good at free surface flows, is not very good at embedded solids, although new functionalities coming out. An unstructured mesh code is much better at specific geometries, and if you have things that require sharp interfaces but won't do topological changes for you. So you have to pick your battles accordingly. It's not just the case that if you pump enough nodes or degrees of freedom into one of them, it'll solve the thing blindly. But with that in mind, and I'll hope to convince you this afternoon, in many of these codes that sort of live, so many of you may have heard of this differentiation between source code and driver code. In a nutshell, the source code is the part of it that has what's under the hood that pertains to things like, say, mesh setup, linear algebra, system solving, preconditioners, things that, unless you really work in numerical linear algebra, say, you may not need to touch too much. And instead, you can inherit from there, and users will typically develop what's called driver codes that then inherit properties from there and use them strategically in an otherwise open source environment. And of course, you can then start, individualizing them and making your own constructions on top of it. But the point is, you wouldn't have to build everything from scratch yet again, because it already has a fairly robust pipeline under the hood for all of these things. And it's the same for Basilisk, it's the same for umflib, it's the same. I've collected a few for this afternoon. I can walk you through them. The idea is that as we learn, we're more likely to interact with the driver code side of things, and for our fluids problems, that would be setting up mesh initial boundary conditions, parameters, what we want as input and output into the system, things like that. And as we get more into it and it becomes a research problem, I may, for example, have to develop a new element for my specific problem, or I may have a specialized algorithm for a particular volume of fluid type method. But I think having this differentiation might help. What I'm really trying to get to is most of the driver codes are a couple of hundred lines, and there's usually quite a few examples out there. So if you're not a CFD or a DNS person and this looks a bit scary and you're thinking, I don't want to code thousands of lines of code because I don't understand what's under the hood that well, there's a starting point into it, and it's more of a, a journey than anything else. It takes a bit of time to learn, but there's help along the way, and for certain problems it can be quite helpful. So I don't think it's realistic for us to assume we'll have fully running codes at 100% by the end of the day, but I'm hoping that you'll have enough in terms of curiosity to maybe drive them home later in time, be it with Basilisk or anything else, to make it useful for you. But that's kind of my rough intro to Basilisk. It's not as painful as it sounds. And what it solves is, the complete set of Navier-Stokes equations, no simplifications. It's doing it under the one fluid formulations, by which I mean this color function that I mentioned is used to navigate between fluid 1 and fluid 2, which can be the drop and the ambient gas, or the pool and the ambient gas. Actually, for our problem, we'll have two different color functions anyway. But you see that there's a rho 1 and a rho 2, and a mu1 and a mu2. The typical difficulty in these problems is how do you deal with the interface? Because when C is 0 or 1, you have a constant value in this case if you're solving an incompressible problem, say for density. But really what happens at interface is C takes values between 0 and 1, and there's quite a bit of discussion depending on what it is, density, viscosity, permittivity, conductivity. You may want to employ arithmetic means, harmonic means, and various filters on top. So for those really interested in this, there's a vast literature on this that I'm happy to go through in breaks. But in most cases, it works quite fine if you resource it well enough, so you needn't worry too much about it. And what it does is it then gets advected with the flow. So if you read through the traditional papers with Basilisk, you'll notice that there's a specific second order algorithm like I mentioned, and through a bit of work you can get it to basically project through a projection method to a Poisson solver for the pressure. That's the difficult part of the code in terms of consumption. Of course, if you employ adaptivity, it will use bandwidth for that and so on, but the really expensive bit is it will sequence the solution process in such a way that you get one big Poisson equation to solve, which is quite nice. Activity time, because I've been talking too much. So we have our little bouncing drop problem, and I want you to have a think as to how multi-scale the problem is. So I'll go back to the whole thingy. New. So it's, same link, same QR code. What I'm asking now is, if you think of what the most delicate part of our problem is, and what the biggest length scale we need to care about is, how many orders of magnitude do you think that is? How difficult really is our problem? And there's a hidden question in there as to what these regions are.
Can you zoom in?
Can you get
Yeah, I'm sorry. Is it enough?
Yeah.
Yay. Very good. I would call you a sophisticated audience or a pessimistic audience, depending on how you want to phrase it. Okay, so for those of you who have already put answers in, maybe if you want to volunteer an answer. So what's the smallest length scale we need to care about?
Tens of nanometer.
Sorry?
Tens of nanometer.
And what does it pertain to?
The
The gas film that's trapped between the drop and the pool. Yes, that is the smallest length scale. Sadly, it's in the tens of nanometers rather than tens of microns.
Yeah, I said
Yeah.
tens of nanometer.
Perfect. Then you're spot on. How about the largest one then?
Millimeter.
Why?
The drop rate.
That's a good start. We definitely need to resolve the full drop. How about the waves coming out of the pool? how much of them do we need to resolve and why? We said in the model we want them to have an infinite extent and so on. We can't do that computationally, we need a finite box. The question is, how would you pick it? You should get trained for this because you're going to have to answer the same questions on your own in the afternoon. So, anyone care to venture a guess what the natural kind of largest length scale in the problem is?
10 times the size of the problem.
That's not a bad start. It is, the way we've designed it, it is in the tens of times the size of the drop. And I think the key bit is, logic-wise, what you want to do is, as the droplet hits the liquid pool surface, it starts emanating waves outwards. And what you want to prevent is those waves hitting walls, be they virtual or otherwise, and then reflecting back and affecting the dynamics that you're after. So what you can do a short calculation on the speed of the spherical waves that move outwards, and how much would it take for them to bounce back, and that is double that, and that is the safe amount that you need for the code. And it turns out to be, a few tens of diameters.
Wouldn't that happen in the experiment, though, the waves?
They would, but the pool itself in the experiment is also quite large. It's in the centimeters or tens of centimeters range. I'll show you, I think I have that movie for the 3D version of the... Yeah, I think we're in luck here because for what we're after, which I'll share in a second, because I didn't tell you what our target metrics were, we're only interested in the one bounce. So basically, for just one kind of movement of the wave and back, I think you can get away with a few tens of diameters. If you wanted, for example, to study a full coalescence cascade or multiple bounces, then you'd be in trouble, or you'd have to design fairly clever experiments and boundary conditions. You have a bit of versatility here, like you can set walls to be Dirichlet boundary conditions, free slip boundary conditions, but in all cases, you'll incur errors one way or another. So I think you'll have to, see what works. A version of the experiment we're setting up now with Dan is through an infinity pool, where numerically speaking, what you do is you can pin the boundaries, the interfaces at the boundary. In an experiment, it basically the liquid level flows just about above the walls, and you get kind of that infinity pool effect where you only see the liquid surface because it's easier to visualize in that respect. So, I think it depends what you want to do and how you want to design the comparison. But my point here is how you craft your computational domain and how you craft your boundary conditions is important. And this goes for most problems you will solve.
So does the grid go to where the boundaries are?
Yes.
But you just put it on a scale that the waves would never reach it?
Yeah.
You still apply the boundary conditions at the walls?
I will still apply the boundary conditions at the walls. I will also use adaptive mesh refinement as much as possible to make sure that as I move far away from the action region, I'll need to dedicate fewer resources. So even if the walls are quite far away and I still resolve everything, the fact that it's slightly less accurate or under-resolved there won't make much of a difference. So it's not quite as expensive. But yes, I'll show you actually, yes, I'll stop annoying you with this and note that, as Yash kindly pointed out, this is a chance for me to link to James's talk as well. Really, if you wanted to do this problem fully and do the coalescence threshold and so on, the type of effects you are after are the type of ones James would have talked about the other day. Like for example, for two pendant drops approaching one another, this tens of nanometers length scales are what James is finding, and his student Peter Lewin-Jones as well, in these types of problems, if you want to predict the actual threshold between coalescence and bouncing. These tend to be, however, for kind of smaller drops and regimes that are a bit less violent of an impact than we're doing in that sense. So we're lucky that ours happens so quickly that the gas film doesn't have time to drain. We're sufficiently far away from this coalescence threshold, basically, that for the purposes of our problem, we won't need to get quite into that level of detail. But if you were to do this, a bit slower, or you are actually interested in predicting the bouncing threshold, this is the type of detail that you'd need. And of course, you'll have to bring in new physics, new implementation, so it becomes a much more difficult problem. It will be difficult to actually fully resolve monolithically, have a code that deals both with this level of detail and the full type of problem setup that I've mentioned. So I think it's nice that you can dedicate specific resources in specific places. I'll come back to that theme in a second. And yeah, maybe for Sarah's benefit, I'll run the movie. This is what the problem looks like, and I'm zooming in. This is about 1/10 of the computational domain.
Radu, you didn't tell us what the answer is.
Oh, the orders of magnitude? I never calculated it. It's in between. So for our problem, we're going in between about a micron, which is what we actually need, and tens of millimeters. Well, yeah, I think you can get away with 6 orders of magnitude, just about. But I think the key point there is it's more than 2, and the problem is difficult. And you've correctly put all of your eggs in the 2 baskets further down the list. So yeah, despite this being an axisymmetric simulation, so 2D in terms of difficulty, the number of nodes is somewhere to the tune of about 50,000. Like, it doesn't sound like that much, but because you need to put them in the right places and the size of the cells is quite different, then you actually have to be quite careful with the simulation setup. So just to note, the criteria I've used is, maybe I'll put it here. Yeah, I've refined with respect to the interfacial location in both the drop and the pool, and changes in magnitude of the velocity and the vorticity then tell you whether you need to refine kind of further away from those regions. So for example, as the 2 approach, it's quite natural to have that gas film region well resolved. And otherwise, as that wave emanates outwards, if I stop it here, you'll notice a fairly pretty pattern going in that direction. And if I leave it long enough, I think I've cut it in the movie maybe, but I have a couple coming up where you actually see it reflected back. By that time, the droplet will have bounced up. And from this point onwards, that's where we kind of get all the metrics. Well, up to that point is when we get all the metrics we need from the problem.
So that's 1/10 of the domain.
That is 1/10 of the domain, correct, roughly.
So do you change the amount of mesh points in time?
Correct. Yeah. And in the afternoon, so will you.
We'll see. Try.
The good news is that is 1 line of code.
Okay.
Can you artificially damp the waves?
You can as well.
So you don't need that much? Or
Yeah, you could artificially, you could basically set it up such from one point onward, you could impose a certain behavior, both in terms of resolution or do something else that's either physical or non-physical. Yeah. But, I mean, it's 10% of the domain, but 99.9% of the difficulty. And actually, I'm not showing it in this one, but it may be visible later. I do have maybe about twice onwards, I decrease the maximum resolution level by 3 or 4. So it looks,
density of
yeah, exactly. So there's ways to do this. Yeah.
One more question. Sorry, you go first.
Go for it.
Yeah, what's the ratio of your domain size to the smallest?
Here I'm getting close to my 5 or 6 orders of magnitude.
So this is your, this will be your answer to that question.
I think this is the answer to, if you know that you're sufficiently far away from the bouncing threshold, this proves to be sufficient to get robust metrics in terms of what we're after. I think if we were to slow this down a notch and it would start coalescing in practice, this wouldn't be enough anymore. Yeah. I think it's, put it like this, it's the suitable resource investment for what you want to get out of the problem. But it's not the sort of tell-all answer for any regime. Yeah. And there's a couple of other things I've been sneaky about that I'm going to be less sneaky about now. I have thrown in a couple of upgrades to the code. One is courtesy of our colleague Vatsal Sanjay at Twente. These are actually 2 different color functions, as I've mentioned before, so they're not allowed to coalesce. If I let them be the exact same color function in the background, even if they would be quite a distance away, they may merge artificially just by numerical standards. So I want to prevent this. So in some sense, I'm using a non-coalescence functionality added on top. I still throw in quite a few grid nodes in the gas film, so this is a zoom in of that particular region. So I always try to keep a few grid cells so that I get a good sense of what's happening within. But it's otherwise it's preventing coalescence altogether.
Even the 2 red ones are different color functions?
Yes, the 2 red ones are different. Yeah, exactly. So effectively, you can think of the droplet as being water 1 the pool being water too, and they're not allowed to coalesce. They have the same density, viscosity, and surface tension coefficient, but they're just different objects symbolically, and they both interact with the ambient gas in the usual way. But yeah, so this has been necessary because if you don't do this, they merge, even when they shouldn't. And yeah, I've noticed that basically the way I kind of stopped how much I go through in terms of resolution level is I've noticed that once the mesh size became about sub-micron, I was getting consistent results in the metrics that I wanted. I think mesh independence is probably a strong term for it. I think errors up to a tolerant level is probably what we can obtain, but that can be studied well, and I'll come back to this in a sec as well. So yeah, so this is what we have, and now the benefit is if you do trust this, you can get all sorts of nice information. So for example, what these plots show, there are two different cases, and they are spatio-temporal maps, so radius on the x-axis, time on the y-axis. Where it's dark, this is the footprint of the drop to the pool. This is the contact radius, so you see that as time goes up, initially the drop is above the pool, it starts coming in, it has a enlarging contact radius, and then as it bounces back up, it starts to lose it, and at some point, after a little pinch off, it bounces. And it's quite flat within, so that assumption of what the pressure field looks like is actually quite decent. And we found that there was a nice recent study from 5 years ago now where they've managed to measure this with a clever experimental technique, and they also found the gas film thickness in this regime to be about 1 micron. So perhaps it was no coincidence that the mesh verification studies and the experimental results aligned reasonably well. But the good news is that once you trust this, and I'll show you the comparative results with our experimental campaign in a second, then you can get this type of information as well as velocity fields, pressure fields, and a few other things as well. So which brings me to the results side of things. If we have a first glimpse into the situation, I'll have another moment. This is the model and the DNS on top of one another. Not perfect, but reasonably close. And I stress that to solve the DNS is a few tens of hours. To solve the model is sub 1 minute. So you want to use the model where you can use the model. Yeah.
I actually had this question much earlier. You did not show your model with this big lean interface curve. It is how it compares with spherical.
We're about. I showed you the spherical harmonics extension as well. That is the bit where you had the weights of the Legendre polynomials to be solved against. That's coming up. Yeah. Basically, I'll now start having sets of plots where I put all three together. So that was, the first one just showed you the model versus the DNS. The experimental figures were on top. And now we can start extracting data from them and have a bit of a play. So the type of metrics, and this kind of brings a bit together. We care about three things in this problem, historically, kind of, in terms of quantities of interest. The easiest one is on the right-hand side. So I think the bottom one was oil, and the top one was water. Otherwise, they do roughly the same thing, so we can focus on one. The maximum deformation of the pool is on the right-hand side. And what you see here, so these are all plots as a function of the Weber number, which you'll notice is quite small, hence the small deformation part of things anyway. And the DNS is in black dashed lines, the model is in blue lines, and the experiments with error bars are in red. So what you basically get to see out of these is there's generally okay agreement amongst them. It's not perfect. There are kind of quirks in each that come from specific assumptions behind each of the approaches or experimental uncertainty as well. For example, I'll point out that actually working with water is very difficult. It's quite easy to contaminate with surfactants, and it's not always obvious how to clean experiments easily after one another. We've made clear assumptions in the model that prevent us from looking into strong deformations, and I've hinted already that the type of deformations we see are kind of at the edge of what the model can do, and the DNS will have numerical errors, and we've put a few assumptions behind that as well. It's the best we could do, but it's not error-free by any means either. So I think to get this type of overlap between them was quite nice. So we see kind of, as you'd expect, the faster the drop comes in, the more the pool deforms. This is the contact time, so how long the droplet is in contact with the pool before bouncing back up. And what you see here is that after an initial decrease, you tend to plateau, and this is quite consistent across the cases. And then the only more difficult one is this alpha, which is the so-called coefficient of restitution. So, in a nutshell, alpha is in absolute value the ratio between the speed at the exit and the speed at the entry of the droplet. So you measure it as close as possible to it hitting the pool, and then you measure it as soon as it detaches from it, and the ratio between the two in that shape gives you this. So for an impact onto a pool where you basically, you bring in kinetic energy via the drop, you lose it via deformations of both droplet and pool, you lose it via viscous dissipation and a few other mechanisms, you'd expect it to be below 1. We find that in both of these cases, it seems to get through either different mechanisms to about a value of 0.3. If you were to impact a solid surface, like a superhydrophobic surface, for example, you can get it to values of 0.7, 0.8, 0.9. But interestingly, we tend to find, as we increase the Weber number, a value of 0.3 for most most parameter studies that we've looked into. And this is a bit of a theme that I'll come back to. But now, yeah,
Can I ask a
of course.
The theory is linear.
Yeah.
So you don't know the amplitude. Do you match amplitudes with the DNS at a certain time and then you let them go together? Or
No.
How do you do a comparison?
I think in both we do it blindly, in the sense that in the calculation, basically when we've picked the point in which the center of mass of the drop is 1 radius above the surface for both entry and exit. Note that this is not perfect because in many cases your drop is still undergoing quite a bit of deformation, which we're not doing south pole or north pole for that reason. But otherwise, basically, we take the DNS data, look at that threshold when the drop goes below it and above it, and do the same in the model, and they'll likely have different contact times, but they're unmatched. They're basically just a measurement of when that level is reached.
But when you show the deflection, there's a linear version and a fully non-linear
Yeah.
version. Then you have to fit an amplitude.
So I think this is the most telling picture. Well, let me start it from here. Yes. So this actually marks the spot where we take the first measurement, and you get to see kind of both in action. They hit, and I would guess, around now is where we would take the measurements for the blue line, which is the model, and the ones from the DNS, which is the dashed line, would have been taken a bit earlier when the dashed line would have crossed this hypothetical. Well, that's what the south pole does. The center of mass has a similar line on radius above. So in some sense, the studies were done independently, as in the model calculations were run, and the DNS was run independently, and we're just, sorry, Sasha, yeah.
Oh, yeah. I understand there are many parameters, right? But also there is initial conditions, right? How you start your development.
Yeah.
Because you can excite some oscillations of the dosage, and definitely they will be excited on their own.
Correct.
But you can manage that.
Yeah.
And then, depending on that initial condition, your balancing or not, it will be different, right?
Correct.
So
Yeah.
there are so many parameters. Or is it possible to state it in deterministic way?
In the DNS and the model, we always input them as perfectly spherical. In the experiment, they're very much subject to the type of issue you mentioned, because as soon as they pinch off from the nozzle, they start undergoing some oscillations. You will have noticed them in the movie I showed at the beginning as well. That was a bit for show and tell, in the sense that the other ones are a bit more controlled. I'll show you another one soon. But they'll still exist, and that is part of the error bar that exists in the problem. So in some sense, the visual error bar is pretty much the tell for how much we can hope to resolve experimentally in terms of uncertainty. However, with the model and the DNS assumptions, we're a bit in a blind spot, because we can only calibrate against one another. So if we put all three on top of one another and are in a happy place, we sleep well at night. If not, we dig further. Sorry, I'll come back to this. Yes, yes.
I also have a small question. For your plot with the coefficient of restitution,
Coming up.
do you find it surprising that it has a local maximum? Is it due to your, does it also exist for a perfect spheric? I mean, why this?
I am not sure, yeah. So, that only happens for really small Weber numbers. You'll notice that the experimental line does trend a bit upwards, but we couldn't find we couldn't take them low enough to be able to see the going down on the other side as well. And you'll notice that, for example, in this one, in the DNS, you also don't see it. The DNS shoots up and the model goes down. So I would call this a reasonably high uncertainty region, where in some cases, like in this one, both model and DNS seem to follow the trend quite well, and we could inspect in a bit more detail, but because the Weber number is so small, experimentally you may start getting coalescence actually naturally there, and it's just not allowed in the model in the DNS, so it may not be a physical element of the problem, yeah. Which probably is why we were focusing on the far end of this problem, and where it goes to slightly higher Weber numbers. Cool. Okay, so if we're happy with these metrics then, the benefit of having the theoretical approaches, both model and computational, is that then we can start taking away effects from the problem. So I mentioned at the beginning, we're not expecting gravity and viscosity to be mission critical, so why not take them away? We are looking now at what we call the inertial capillary limit of the problem, so 0 on a sort, 0 bond number. It just has surface tension and inertial F. And what you see for the same set of parameters as before is a similar trend for the maximum deformation of the pool, a similar trend but much neater for the coefficient of restitution, so this to be visually compared with that one. It's a faster descent if you have good eyes, and it's a very kind of a straight plateau, but it kind of shows you that actually these are the key mechanisms in the problem. So we try to explain and do in this study any sort of inferences on what the energy mechanisms are through this type of system, which was quite nice to do. And then you can play the fun game of asking, well, I've derived my model and I said that my honor-surgeon number has to be small. How small is small? And it turns out, so for example, these are both, this is the plot of, so the colors indicate the honor source number here and the bond number here. The lines are all model and the symbols are all direct numerical simulations. Recall each of these are 50, 60 hours of runtime. So this has been burning clusters, partly in Imperial, partly in Oxford, partly in Warwick for a while. And the take-home message of this is that dots overlap with lines for as long as the honor source and the bond numbers tend to be up to about 0.1, 0.15. And then beyond that, they start deviating quite a bit, where you start seeing these type of discrepancies for 0.2 and above type of values. So how small is an honor source number, or how small is a bond number? That's small in our definition, this small. And it's quite nice to be able to make that distinction in many problems, because we often derive things saying we have a sufficiently small epsilon, whatever that means. Here, if we have this type of system, we can really ascertain where that point is. And of course, it'll be parameter dependent, but quite often, actually, kind of thinking back over the years, we found that modeling approaches tend to be valid for more than we expected. We were thinking, maybe this works for about a value of 10 to the minus 2 of epsilon, and actually the model validity went on for an order of magnitude more. And yeah, in this case, I think values of 0.1, 0.2 are also quite high for this problem anyway. So it was nice to see that despite all of the simplifications and despite the linearization, at least for the metrics we were after, it worked quite well. And if you collapse everything into one big picture, this is what you get. So these were the same lines as before for the coefficient of restitution, and peppered along all of these are all of the experimental studies we knew about up until 2023 when we did this figure. And they seem to all align roughly in this respect, like it's a descent towards a value that's about 0.25 to 0.3 somewhere. The lines here are idealized because this is the inertial capillary limit of the problem, but you see that there's a bit of a trend. The only thing I don't know how to tell you, I mean, for a specific case, it's very easy to look through the output from the simulations, and I can tell you exactly this amount of energy goes into the deformation, this goes into viscous dissipation, but I don't have an analytical reason for why this value needs to be 0.3 or 0.25. yeah, I wouldn't be able to tell you a priori through a formal derivation that should be the case. So if anyone has any ideas, I'm all ears. It seems to be consistent across all bits of the literature if it's a liquid-liquid impact. If you impact solids or other things, then of course the story changes. But canonically, this seems to be quite a strong trend, and we're still exploring this. Cool. So there's a few things that we've alluded to that may be worth fixing in terms of the modeling assumptions, in terms of the DNS accuracy, and so on. One that we talked about was also kind of how close the walls are, and the bit with the infinity pool that I mentioned was actually because we were trying to look into if you bring the walls close enough, or enough so that you actually do get wave reflections back, there may be a mechanism there to use constructive mode interference and so on to actually get a higher coefficient of restitution if you want to, or a lower one that suppresses the type of dynamics. So we're trying to do this in a systematic way, and this is why that came to mind. And quite often you would have things like surfactants, non-Newtonian fluids. We did this with the same liquid in the drop in the pool. It doesn't have to be the case. So there's a few extensions even from there. And 3D might be an interesting kind of side to this problem. So I think we mapped quite a bit of the picture in axisymmetric mode when the impact is 90 degrees. What would happen if that's not the case? So I just thought I'd finish this problem with what we're currently doing. I'll show you 3 movies just so that you get the gist of it. So this is a quick phone movie of Dan's lab setup with the actual nozzle, with the actual setup. And what's happening here is the drop generator is actually fixed, and there's a moving pool underneath it. It's a rotating table that's huge. It's meters long. And it's a kind of a simulator for a moving pool being hit by a drop at 90 degrees. But it does have a symmetry breaking mechanism in there. So if I show you a more professional movie taken by Dan, that's not me messing about with the phone in his lab, this is the type of, the lighting is not great, but basically in here you see that the droplet doesn't actually deform too much on impact, but then it does, and when it hits the pool, and if you can follow the line of the drop, you'll see that the wavefront is differentiated on the 2 sides because the pool is moving in a particular direction. So we found that in certain regimes, of course, this is equivalent to a static pool being impacted by an oblique drop. So this is what I mean by the 3D effect of this problem. So now we're trying to explain this by kind of looking at the gas film thickness and having to modify the coefficient of restitution study to account for the fact that there's not just one exit velocity, but it's the vector with multiple components as well. So there's, loads of fun things happening in this problem space. Cool. If you're curious about more, ask me. I'm going to be around until tomorrow, much of it, and then I'm coming back next week, Wednesday to Wednesday. So I'm happy to sit down over a coffee and tell you more. There's a couple of papers that go with this. It turns out that if you pick your color scheme strategically, you can get cover photos in JFM. Just a subtle tip, which was nice. And I think that's where I want to stop with the bouncing drop part of the problem. And now I have 10 minutes maybe to introduce the splashing problem before we have to break for lunch. Yes, Sasha?
May I ask about the bouncing?
Of course.
It seems that the same could be expected for H spheres.
Yeah.
But actually, intuitively, I cannot imagine that it's bounced from liquid. Why? Is it special, something special with a liquid that is bounced from liquid? Or it's also possible for rigid?
It's possible for rigid ones as well. Yeah, the first paper here is all about solid rebounds.
So, okay.
It's done with that super hydrophobic coating I mentioned, because as soon as you get the pool interface to touch the sphere itself, it'll submerge it. Basically it becomes like the contact angle from the pool starts rising up on the solid, and you get other types of interactions. But basically, as long as you can maintain a gas film between the impactor and the pool, irrespective of what the impactor is, and there's enough energy in the system so that the dissipation into the deformation and viscosity and so on doesn't completely eliminate it, you'll have enough on the way up to do a full bounce. Yeah. It will be actually interesting to compare them side by side. We've done them as separate studies, so I've not actually looked at exactly the same parameters super hydrophobic sphere versus, but we're still in touch with the whole team, so this might be an interesting group. Cool. Bit of splashing. So we care about bouncing, by the way, apart from the fact that it's a beautiful phenomenon and it kind of teaches us about quite a few things. There's kind of a fundamental interest because of the so-called hydrodynamic quantum analog studies. There seem to be some similarities between what happens in the macro scale space with classical experiments in the quantum space. So if you have a vibrating pool, there's a lot of studies dedicated to this in the recent years. But you can also do things like energy harvesting and other types of kind of more lab-on-a-chip device type systems with them. If we go to much higher speeds like splashing, this actually has a richer history because people have cared about these for a while now due to more modern applications are things like inkjet printing, pesticide distribution, and so on, preventing aircraft icing. But over the years, because it's such a beautiful phenomenon, it's seen a lot of historical attention as well. And in particular, it's about 150 years old or so now. This is the first experimental study that's been logged on splashing droplets. The setup has two arms because what Worthington did is he was releasing a droplet of a very carefully measured size from one side and a marble of the same weight from the other one in a dark room. And as the marble touched the floor a bit before the droplet, it basically lit up the room enough such that early photographic equipment, 1870s, was enough to be able to capture glimpses of what was going on, and then he was able to sketch the splashes in question. Incidentally, these are modern realizations of the same kind of experimental setup, and you'll notice that they're missing these types of finger instabilities that you see here, and folks have attributed these to the presence of surfactants in the lab that would have been very difficult to know about and clean back in the day. So just to know that, splashing droplets are really nice, and there's a kind of a good history to this problem. And the theoretical framework for this that's been really successful since the 1930s really is the so-called Wagner theory. It was designed initially for applications such as aircraft landing on water or ship interacting with things like waves or ice caps or things like that more recently. Sasha has made significant contributions to the field over decades now, I think. In general, I think it's seen a bit of a rebirth in the 90s and 2000s when it kind of was repurposed as well for smaller millimetric drops. But I've still met people who, like at the Basilisk user meeting a few years ago, a company from Norway came in and they're using Wagner theory estimates for offshore facilities to estimate the pressure from waves on their sites to be able to do structural damage estimations and so on. So it's still used in some sense in the original sizing, but it's seen a bit of activity for much smaller scale impact as well. And these are the list of assumptions that go behind this problem. What it basically says is you throw everything away except geometry and inertia. No surface tension, no viscosity considered at this point, no nothing. And with my colleague Madeline Moore, who is actually coming next week for the conference, we've worked at this while we were at Imperial Oxford and more recently as well. I'll kind of give you the full story of it. And the first bit that we did was for 2D problems, but then extending them to asymmetric impacts. So droplets of different radii or different velocities hitting one another. And this then kind of gives you access to these types of scenarios where basically you can go all the way to impact onto a liquid pool. So this is the infinite radius, distinguished limit, and zero velocity ratio, but you can have anything in between as well. And kind of trying to do this systematically, getting good compact estimates from the Wagner theoretical framework and getting them verified with DNS to establish their range of validity yet again. And I think the last point I want to touch before the break is the structure to which you do this is you have an existing structure that you assume that is already a formed splash, like this is the drops have hit one another. There's the root of the jet that gets splashed outwards, and there's the jet itself. Because we don't have surface tension involved and so on, there's no capillary tip or anything like that. It's just inertia. And you then take the three asymptotic regions that result from here. So there's the outer region that keeps the shape of the droplets. But if you then zoom in, you actually get a breakdown close to the root of the jet that hints towards you needing a new asymptotic region there with different considerations. So you get this inner region, which is an order below, and then you get a thin, long region along the jet that requires its own treatment as well. And it's a combination of asymptotics, complex analysis, and PD type of techniques that I've hinted to here. Maddie always hates me when I do this, but I'll do it in 3 slides. It takes 70 pages of derivation. The 3 slides, one for each region, are, for the outer region, we find our lovely friend the Laplace equation, yet again, in both sets of fluids. And the root of the jet is seen as a moving point here that has this particular type of singularity that alludes to a new structure being needed there. If you then zoom in, you get a free streamline or a Helmholtz flow that once you put it in the right frame coordinate-wise, you can get estimates on the thickness of the jet and on the velocity along the jet. I'll just remind you that R and V are the ratio of the radii and the velocities. They're all constants. So these are actually quite friendly expressions. And finally, if you go to the jet region itself, you again recast it in friendly coordinates. And after that, you get zero gravity shallow water equations. You turn on your favorite method of characteristics for it, and you can get closed form answers for the velocity and the thickness of the jet. Now, just before we break, I think philosophically speaking, I quite like this problem because I'll remind you that this came about in the 1930s. If we kind of think of what is the most classical matched asymptotic expansion we know about, I would argue one would think, for example, of boundary layer theory. And if you think about kind of your classical, you have your aerofoil, you have an oncoming flow, and you hope to look close to the leading edge. And if I zoom into that region, you'll have, free flow on top, and somewhere here there'll be a structure that looks something like this, where you have to match the no-slip condition at the bottom with the, effectively the U is 0 here with the U is equal to 1 there. And this will be the solution the Blasius solution and so on. It's a problem with kind of an interesting history in its own right because this was the early 1900s, and I'll share something in a second. And the iteration to this, so what happens if you want to take into account a small obstacle on the surface like a rivet or something, so say there's a little bump or similar here, in order to deal with this, even if it's a small height, the solution for this is called the triple or the multiple deck structure. It doesn't look too dissimilar, but instead of having region 1 and region 2, say, this one actually gets 3 regions, 1, 2, and 3. It's still U equals 1 up top. This is a viscous sublayer where the flow profile is linear, and this is a viscous inviscid interaction region where pressure information gets exchanged across. This was roughly 1960s. This was roughly 1900s. And that's somewhere in the middle, and it's quite a complicated problem that I like. The thing I wanted to tell you about the boundary layer history, there's a nice little study that came up 2005, and I've just highlighted a few paragraphs. So this was presented by Prantl in 1904 in Heidelberg at a meeting, and the presentation was 10 minutes long, and it took years for it to permeate through the community. And you'll notice some of the things that plague us in our current kind of conference activity as well. Like, for example, the bit I highlighted here. In 1928, Stephen Goldstein asked why the paper was so short. So Prantl replied that he had only been given 10 minutes. So he thought the paper should encapsulate only what he can say in 10 minutes. So it's just a few pages long. And after that, through the work of himself, his students, and kind of the community as a whole, it permeated through. I noticed a bit of passive aggression at some point in this. There's a little line here that says, information flowed much more slowly at the turn of the century. The Third International Mathematics Congress was an obscure setting for such an important contribution. So I feel physicists and mathematicians were still working on their interdisciplinary prowess, is how I put it.